Hello everyone, welcome back to another session of Getting Started with R Programming. In our last session, we have explored the basic syntax of R. We also looked at how conditional statements like if else work and also introduced a loop structure briefly. In today's lecture, we will build on that foundation and move to the next set of topics that are very important for practical coding in R. Here, what we will cover in this session, we will learn about some basic operators in R. These are the essential vocabularies you need to understand first before we jump into the complex programming or complex functioning, complex data analysis pipelines. Next, we will understand some data structures in R, like we learn about different data types, how R works with different types of data like logical, numeric, factor, and character data sets. Similar to this, we have different types of data structures. In that way are organized or store information in it. Till now, we are working with the R built-in function that already built in R, but in today's lesson, I will teach you how you can customize your own R function, so that will help you to avoid repetition of your data analysis pipelines when you have to repeat different tasks again and again. And to wrap up this session, we will look at how a for loop function will help us to automate our work. Like if I have to repeat all the analysis pipeline for 4 to 5 data sets, and I have built the pipeline of 100 or 1000 of a line. So for next data set, I will not rewrite or rerun all the lines again one by one, but I can automate my work using loop function. So in this session, we have quite a lot to cover, but I will keep using simple examples so that all the concepts stay clear. Because after that, we will apply the same ideas and same concepts on gene expression data analysis or machine learning pipelines in our next modules. So let's start with the first topic, that is operators in R. Basically, operators are the simple symbols that tells R to perform some action on the values or variables. So without operators, R would not understand how to handle number, text or logical conditions. Let's start with the first one, that is assignment operator. You are already familiar with this assignment operator. So what assignment operator does, it let us store values in variables. To assign values, we have different types of assignment operator. You already know this, how to create variable using this assignment operator. So first we have to define the variable name. Let's say I want to create a vector height to store the height of the patients. Similar to this rightward assignment operator, we have another leftward assignment operator that is opposite in direction to this rightward assignment operator. When we use this leftward assignment operator, so first we have to define our values that we want to store in that particular variable. So in case I have also measured the weight of these individual, or I want to create a new variable with the name weight. So first I have to insert the values like 68, 78, 85 and 75. After values, now I have to insert this assignment operator, that is hyphen and greater than sign. Now after this assignment operator on the right hand side, I have to add the variable name that is weight. So it is totally opposite of this assignment operator. If I run this line of command, a new variable weight has been created. You can also use equals to sign to assign variable name to a values. This equals to operator works similar to this rightward operator. So in this case, again, first we have to assign the variable name. Let's say I want to assign the smoking status of the individual. Let's say smoking status equals to sign, and values for the first individual it's yes, second no, third again no, and fourth one is yes. So in this way we have created three different variables using three different assignment operators. You may find some other assignment operators, but we are not discussing them here. So you can use these assignment operator to assign values, but this one is this rightward assignment operator is most frequently used. It's standard in R programming. So stick to this one to avoid any confusion or errors in your code. Next we have arithmetic operators. These are just the mathematical symbols that we use to perform some calculation. So you can use R as a giant calculator. We use these for addition, subtraction, multiplication, and so on. For example, let's calculate the BMI using these weight and height variable. So to calculate BMI, we have formula, that is weight of the individual divides by their height square. So in this equation, I have used two operators, two mathematical operator. First one is this division that divides weight by its square height, and the second one is this caret for the power of 2 that calculate the height square for all the individual. Okay, let's run this line of command and get our output. Notice that how R automatically calculates BMI for every value in the vector. So this function is called vectorization. Like, it means R perform addition to every value in the vector. So in that way you don't need to specify the any single values. By using this vectorization, R perform function on the entire data set. So next we have comparison operators. Okay, we calculated BMI using mathematical operators. So but we want to ask, is the BMI is healthy or is it high? To ask this question, we use comparison operators. Basically, comparison operators don't calculate any answer, rather than it compares the values. Like, is BMI is greater than 25 or it's less than 18.5. For these both statements, BMI greater than 25 and BMI less than 18.5, output in the form of a logical vector true and false. So basically these comparison vectors ask yes or no questions. In R, if the condition is yes, so the output is true. Yes means true and no means false. So in this case, the first BMI is 22.2, that is less than 25, so the condition is false. The next one is 25.1, that is greater than 25, so condition is true. For the third and fourth, the BMI is greater than 25, so the logical condition is true. Similarly, when we ask if the BMI is less than 18.5, so in this case we don't have any value less than 18.5, so all the logical conditions are false. So in this way we can use these comparison operators to filter out and find some important information from our data sets. Sometimes one question is not enough for us. We want to evaluate based on different conditions. For example, is the patient is overweight if their BMI is greater than 30 and a person is a smoker as well, to evaluate the risk factor for the diseases. So, to evaluate our data based on different conditions, we use logical operators. These logical operators help us to combine multiple conditions. We have a different types of logical operators. Here we look at these three examples. Now let's see how these operator works. First, we have a question like is the patient overweight and overweight and a smoker? You can use these operators as a boolean operators, like in when we search our data in databases, we use this AND operator to get the both conditions true. So in R we use AND symbol. So this is our first statement: is the patient overweight and smoker? In terms of the R we write like this: in first bracket BMI greater than 25. We have a standard cutoff for BMI, that is 25. Above this threshold, we have the category for overweight. BMI greater than 25, this is our first condition and symbol. Our next condition is the individual is a smoker or not? Smoking status equals to, here note this two equal sign, this is different to the that assignment operator. If you use this single operator, it means you are assigning a value. But if I insert another equals to sign, it means I want to compare the value or I want to obtain exact answer. In this case, I want to check the yes status, if the person is a smoker or not. If I run this line of command, the output is first three conditions are false and last one is true. What that means, in our data set, we have only one individual whose BMI is greater than 25 and who is also a smoker. So if I revert the condition at this time, if I say that if BMI is less than 25 and smoking status is yes, I want to check if the person have the BMI is less than 25 and in a normal range, they are a smoker or not. In this condition, we have a participant, one participant with normal weight and smoker status. So in that way, we can subset our data set. Let's check another condition with some flexibility, like is the patient is overweight or a smoker? So in this time, R will check both condition. Any condition is true, then returns the true. So to write this BMI greater than 25, or using this pipe operator, we are saying check both condition. Either of the condition is true, then the output will be true. Smoking status equals to condition is same, but we have changed our logical operator. Then run this line of a command to check the output. So at this time, what R did, it checks the both condition and return true. This is our BMI and this is the smoking status. So the first condition is BMI greater than true, BMI greater than 25. BMI is 22.2. This is false, but the second condition is true. So the output is true because the second statement is true, person is a smoker. So second statement is BMI is greater than 25. So it is 25.1. First condition is true. This first condition is true, but the second condition is false. Still our return true because first condition is true. Similar to the third condition, we have BMI greater than 25 and person is non-smoker, but the since the first condition is true, so this OR operator return the logical answer true. So it is more flexible than the this AND operator. For AND operator, we need both conditions true, but for this, we need only one condition true. Next, we have a NOT operator, so we can ask a question like this: is the patient not a smoker? Reply is not. Smoking status equals to what? No. So in this case, we have first statement true. It gives you a revert answer. Condition is yes, then the output equals to false. This is the minor difference of this not operator to the other logical operators. In this case, if the condition is yes, true, then the output will be false. But in above cases, when we have the condition equals to yes, we had output true. So, a person is a non-smoker, the output will be false. Again, person is non-smoker, the condition is true, but the output is false. The person is a smoker, condition is false, so the output is true. So that's all about the operators of R. Now let's move to the another topic, that is data structures in R. In a real biological data sets, we don't just store a single number like 4 or 5 values. We usually work with thousands of patient records, gene expression values, or metadata. So you may have a question: how does R organize and store all these big data sets, and how we gonna work with? So the answer to this question is data structures. Data structure is simply a way to organize and store our information in R so we can work with it. Let's start with the simplest one, vectors. A vector is the most basic data structure in R. Think of it as a sequence of value, all of the same data type. Like we have different types of a vector: numeric, character, and logical vectors. You are already familiar with these data types. For example, numeric vector, all are the numbers. These are the numeric vector. If I check the class of this vector, so it is numeric. We use numeric operators to perform mathematical calculations. You cannot perform any calculation or mathematical operation on your character vectors. What are these character vectors? These all contains text or a string data like gene 1, gene 2, and gene 3. We can create logical vectors as well. So logical vector contains only true and false statement. So notice how every element inside a vector must be the same data type. That's why this structure is so strict. Like if I want to create a mixed vector using numbers and strings, I want to create gene 1 with its value, that is 1, is gene 2 with its value 2. And if I run this line of command, R creates a vector, a mixed vector. But if I want to perform any function on this mixed vector, like if I want to calculate the mean of this mixed vector, so I cannot perform any operation on. We can access the element of any vector using indexing with these square bracket. Let's say from my numeric vector, I want to access the elements number 2. It will give the output. Similarly, I want to extract the value from the from element 2 to 4. Now it's provide 3 values, that is from 2, 3, and 4 element. This semicolon indicates equals. In this way, I can pick specific sample gene or values from a large data sets. Okay, so we already discussed that in the vectors are the strict. We cannot create mixed vector like we tried here. But unlike vectors, we have a list that is more flexible than the vectors. You can store multiple data structures and data types in list. We have created these 3 vectors: numeric vector, character, and logical vectors. We can store all these in a list by using list function. So we have a list of 3 here. If you check, we have the numbers, we have character and logical. Another difference is that can only combine vectors of equal sequence. To combine vectors, we have two commands. We can treat vectors as columns. So combine the vectors in a column, we have a function cbind, that is column bind. I want to combine this numeric vector and character vector. So first I assign the value numeric vector, then this character vector. It combines, but what it did, it duplicates the gene1 value from the character vector. So when we combine unequal length of the vectors, it will duplicate the values or maybe throw an error. But when we combine the unequal list of vectors, when we combine vectors in the form of a list, so it all the vectors remains unchanged or remains in their original state. So in list we can store multiple things, like in list you can store your raw data. Next you can save process data within same list. Also you can save your results as well. Okay, and to access the element within a list, we use these double square brackets. If I want to get the second element, so I insert this second. The output is this character vector. It shows the output for the second element. Or we can save this into a variable as well. Next, we have a matrix. A matrix is the two-dimensional data with rows and columns, just like an Excel sheet, but the rule is same as the vector. All values must be same, usually numeric. Okay, we can create a simple matrix function. Let's create simple matrix with 3 columns and 3 rows. We have created a matrix using with 3 rows and 3 columns. By default, R fills matrix column wise, but we can change it by using the function by row is equals to true. So in this way, I will create another matrix with my matrix 2. Okay, so here if I assign by row equals to true and run this line of command, set the output. Now we have values by rows. First we have by columns. It filled the first column, then second and third. But when we assign by rows true, it start assigning values by row wise. First column, first row, then second and then third. So in this way you can create your matrix. Again, same like vector, we can access the element using a square bracket. Like my matrix, if I want to extract row 2 and column 3, and if I run this line of code, so it return only this 6 element, that is row 2 and column value of column third. Similarly, if I want to extract all the values from row 2 of all these columns, so first I have to mention this 2 I want to extract from the row second row, and then I will then I insert this comma. After this comma, I will not specify anything. It means R will extract values from all the columns. So now at this time, I have the value for the row number 2 for all these 3 columns. So the rule is simple. When we have a matrix, and we want to access any element using indexing. So before comma, we can extract rows by specifying their number, and after comma, we can extract columns. Now let's move to the another data types, that is data frames. And a data frame is a table where each column can be a different data types, unlike matrix. Matrix have limitation that everything must be the same data types, but data frames are flexible. In data frames, we can store anything. We can store different types of data like numeric, character, or factor data sets. So you can store all different data types in data frames. Okay, if you want to create your own data frame in R, we have a function like data.frame. First, let's say I want to create a column for patient ID. Patient ID equals to patient 1, patient 2, and patient 3. These are the values that will be filled in this patient ID column. So age column again has the same number of elements. We have 3 patients, so ages must have a same columns, same values. If we have any missing data, we have insert NA. It means not available values or a missing value. Next column is diagnosis. This looks like a typical clinical data sets. Each row is a patient and each column is a variable. So typically we have biological data sets in that sequence. Like we have patients in the rows and we have their features as columns. For any data analysis, it is important to assess the data structure and to check to do some fundamental data assessments, like to check the structure of the data set. STR function structure tells you the data structure, that is data frame. Next, against each of the next, we have 3 observation and 3 variables. It means we have 3 number of rows, 3 observation and 3 variables, means 3 columns or 3 features. And against each column, we have their respective data type. So we can check the structure of a data set by using str function. Next, we have a head function that help us to extract the first 6 rows. In this case, we have only 3 rows, so the output is entire data set. But in real data set, when we have a more than 10 samples, it prints the first 6 rows. If I specify I want to check only first 2 rows, so n is equals to 2. So now it only prints these 2 rows of the actual data set. Similarly, we have a tail function that prints the last 6 rows. Here you can also specify the number, like data n equals to 1. It will print the last row. If I say n equals to 2, so the output is last 2 rows. So next we have dimension. We can set the number of rows and number of columns of the data by using this dimension function. So in this case, we have 3 rows. The first element indicates number of rows and the second element indicates the number of columns. Similarly, if you want to check the names of your columns, so we have the function names. It will print the names of all columns in that data. So this helps us understand what type of variable we are dealing with. Similar to the matrix, data frames are indexed like a matrix, but with a little more flexibility. Like you can access a column directly by using selector function. By using selector, this dollar symbol. So in this way you can specify any, you can access any specific column of your data set. You can also access by using indexing. Like if I want the data value from the row number 1 and 3, column number. So we have value of the row number 1 and 3 and column number 2 and 4 of our data. The first column is patient ID column, but using this indexing function, we exclude this first column. So in real world setting, the reality is no data set is ever perfect. We always find some missing values, some missing information, especially when we are dealing with gene expression data sets. Sometimes we have the gene expression values of the all patient, but we miss the some clinical information, like either patient have cancer or not, we miss that information, or some other clinical parameters. So in R, these missing values is represented as NA. If we don't handle them properly, they can ruin our calculation. So let's look at how R deals with missing values. Check the missing values in our data set. We have the function is.na. It will return a true, means the value is missing. We can also check missing values per column. To count the total missing values, we use a sum function like sum, then again is not na into data. So it will calculate the total numbers of total number of missing values from our data. So in this case we have only one missing value. We can also check the sum of missing values by columns using column sums function. Column sum, same statement is.na, then data. It will return the missing values in the column. So the output is now column wise. In patient ID column we don't have any missing value, zero sum. For the age column we have one missing value, and for diagnosis we have a zero missing value. Similarly, you can identify missing values in your rows. Missing values by rows using same raw sum function. Raw sums is dot na and name of your data. So in the third row we have missing value. Once we know where missing values are, we can decide how to handle them by removing rows or by removing columns, or replace the missing values with something like mean. So to remove rows with missing values, clean data 1 and then na dot omit of my original data. So it removed the third row which have a missing value. Similarly, we can remove columns that have missing values. To do so, create another variable with data2, clean data2. Then here the original data set where we want to remove columns with missing values, that is data. Then we index which column sums is dot LA. So in this way, we can remove columns with missing values in our data set. So if we check the structure of clean data 1 and clean data 2, in both cases, we lose our data or information. Let's imagine we have a data set with more than 50 rows of missing values. If we remove missing values by rows or a column, we end up losing some information for our data sets. So instead of removing columns or rows from our data set, we use a strategy to impute missing values. Like sometimes we replace missing values with 0 or replace with the column needs. So to do that, let's impute the value with 0. First, let's create the copy of this data. Now, from this clean data 3, we replace NA value with 0. Result NA from clean data will replaced with the value 0. So, if we check the output of clean data, this is our original data with LA value. Now we replace the LA value with 0. Similarly, you can equate value with function. To do that, again, create a copy of original data with name clean data 4. Now at this time, this condition will remain same. Instead of a clean data, we will add clean data 4 because we want to make changes in our clean data 4, not in 3 or in our original data. So we will calculate mean of the column for the missing value. We have missing value in the age column, so we will calculate the mean of data age column. Here, important thing is to remember, you have to specify this na.rm function. That means remove this na from the data and calculate the mean. If you don't specify this condition, R will throws an error because with na, R cannot calculate the mean. So, if I run this line of command and print the output of this clean data 4, so now at this time, instead of a NA, we have mean value of this age column, that is 71. So that's all about the data structures. Up to now, we have been typing codes directly in this R script by using built-in R functions and operators. That's fine for a small task, but we are doing so far. But in data analysis scenario, like in bioinformatics and machine learning pipelines, we have to repeat the same steps across many columns, and even we have to perform the same steps with different types of data sets and files. Instead of copying and pasting the same codes again and again, we can create our own customized R functions. These functions allow us to package code in a reusable blocks. Like we can combine the 4 or 5 line code into a one customized function and we can run them again and again. So the function is a reusable block of code to 4 elements. First one is its name. Like if you want to calculate the BMI of the individual, so the function name should be the representative of that function. Like calculate BMI. This will be the function name. So to create custom defined functions, we use a function keyword. Within this function keyword, we place our input argument. Next, we have the body of our function or the operation we want to perform it. Like in case of BMI calculation, we want to calculate the BMI of the individual. So in this case, we have the function that is weight divided by height squared of individual. The body or the statement operation step enclosed in the curly brackets of our function. Next, we have the return value that we specify by using this return function. So in this way, you can organize your own data analysis pipeline by creating customized function, or if you need to use this function like for another project, you have to calculate the BMI. So you can call the function and you can use that function. Create our function to calculate BMI. Create a function to calculate BMI. First is the function name, that will be calculate BMI. Next, we use function keyword to create our function. So inside this function, we have two arguments. We will mention weight and height within these parentheses, and notice that these are the dummy arguments or inputs. These are not the actual values, so these are just the names. So instead of a weight and height, you can say anything like W and H, but if your function need two arguments, you have to mention 2, otherwise R will throws an error and will not create your function properly. So after that, we will add the curly braces. In these curly braces, we have to mention our function or the operation we want to perform. What we want to perform? We want to calculate BMI. So we create a BMI variable here and insert the formula, that is weight divided by height squared of individual. Next statement is what we want. We want the output as this BMI variable. If I run this line of command, okay, here under this function section, we have created a new variable with calculate BMI. So at this time, we just create this function. We don't perform any calculation or any operation in it. It is just a simple function. When we call this function, it will calculate the BMI for the values we provided. Let's call the function calculate BMI. At this time, I use this calculate BMI. So here you can see we have parentheses here. So this is our customized R function. Here you can see it's stored as a variable name, but when I call it, it shows with the parentheses. It means it's a function. Now, what we have to provide here? So here I had mentioned 2 inputs. So I have to give 2 inputs. Let's say first is the weight equals to, this is this weight equals to, now I will add what 60, then comma, this height equals to, let's say 1.75. use these height and weight columns again, what we have created earlier, weight and height column, to calculate BMI. Weight equals to this weight, the variable, and the height equals to the height. And if I run this line of command, so at this time I have the same output which we get from this BMI. So I get this same output which we earlier had, but what happens if I only pass the one argument, like just a value for the weight? So it R throws an error and tells you that argument height is missing with no default. So if you don't want to use any value here, you can specify default values. Like if I say height equals to 1.75 and run this function, at this time R will take 1.75 from the function value and divide it with its weight. We can use default values when we want to specify any threshold. So the important thing is that if your function is expecting 2 arguments, you have to pass these 2 arguments. Otherwise, R will throws an error. Similarly, if we specify 3 arguments, but within our function body we use 2 arguments, R will don't care about the third argument. Let's say if I create a new variable and at this time calculate BMI 60 and 1.65, R simply calculates the BMI of these values because in our function we didn't use this age parameter. If we use anywhere this age column to calculate the mean or something, anything else, so R will expect the another element here as well. So in this way you can create your own customized function. This is the very basic concept for creating function. You can add multiple lines of code to create your reusable block. So now let's move to the last topic, that is for loop. Suppose we have multiple data sets. For that we have to calculate the BMI. So we have the original data sets in our working directory. So to calculate their BMI, first we have to import them into the R. This time I have 2 data sets in my working directory. My main working directory is R programming. Within that subfolder raw data, I have 2 data sets, data 1 and data 2. I want to calculate BMI. To do so, first of all, I need to import both of them in R. Then I have to perform some data assessment like checking the NA values and remove all the NA values if exist. So after data cleaning, I will perform BMI calculation for each of these data sets. Next, after calculation, I have to save these results. So instead of repeating these steps for each data set, we use a loop function. To work with the loop, first of all, we have to define our input and output folders, like from where R will take my files and from where it will save it. So we will start by defining input folders where raw data is stored and output folder where clean files will be saved. In my case, my input directory, this raw data folder. So here I just insert the name of my working directory. It is not actual folder but the name of working directory. So you have to make sure you don't have any typo here. Like I did a mistake. I have raw R capital and D is also a capital, but I insert in lowercase. Next, I want to save my results in this results folder. So now my result folder is empty. I will save my results in that result folder. So the output directory will be results folder. Next, we have to check if the output folder exists or not. If not, so to ensure we create output folder, To do so, we specify the condition if not operator directory dot exist. Remember this not operator, this will check the reverse condition. In case of a no, it will create output directory. I will specify it as output directory. We'll give the command directory.create. If you remember, we use this directory.create command to make subfolders in our working directory. So here if I insert the output directory, what will happen with this line of a code? This if condition checks if output directory exists. If not exist, opposite in the case we have assigned this condition. If not exist, then create working directory as out directory. So R will read the value from this output directory, that is results. So end result is the results folder will be created if already not exist. Next is another important thing. We have to specify which files we need to process. As you can see in my raw data folder, I have multiple files, but I said I want to calculate BMI for this data 1 and data 2. So there we will specify the file names which we want to process. So here we tell R which files to process. Like I want to process only these data 1 and data 2 PSK files. So files to process, R will automatically import my files using the loop function. So I will just mention the names using this C function. So with these names, R would import files from the raw data folder. So in this way, when it is specified the file name, R will only import the specified file. And the next step is we want to store our results in our environment to check the output. So to do that, we will save our results in R. First, we will create the empty list with the name result list. You don't need to specify anything within this list. When loop will run, R will automatically save the results in this. Now let's create loop function for all of these steps that we want to perform automatically for data 1 and data 2. So to create loop, we use this for function. Here in variable, I named extra name again, and in vector I will pass these files to process. So when we are working with loop function, the important thing is we want to track our progress, how loop is working. If we have any error, any type of mistake, loop will stops immediately. So to ensure processing at each step, we can add a cat function that works like same as print function, but you can specify or you can customize your function. It will just pass the message with customize outputs. This n will ensure that number of files. So the complete message will be processing data 1 CSV file, then R will processing data 1 CSV file. And so data 2, it will be data 2 file names. So in this way, we can track our progress within the loop. So now we will mention the file path. For file path specification, we have file path function. Here within this function, we will mention our, we mention our input directory from where R will get the files. So with these names, R will import files from the raw data folder. Now the next step is import dataset. To do so, first we create a variable data. Then these are the CSV files. So I will assign a read.csv extension to read these files. Then this input file path. This will helps to import the data from raw data folder. Say header equals to true. If files imported, file imported, checking for missing values. After file will import, we have to handle missing values. So to handle missing values, we specify the conditions. If height, column, names of the data have missing count. Okay, first we need to check missing values by using this if condition. It will check if we have any missing data. So missing count of the sum is dot NA. Okay, make sure one thing, we are working with two data sets, so both column names must be same. Like this height and weight column, in data 1, we have height and weight column in lowercase. Let's check in the data 2. We also have height and weight column in lowercase. If the column names are not same in the data sets, R will throws an error because we are creating the journal loop that is not specified to any specific data but for both of data sets. So column names of your data 1 and your data 2 must be similar. So in this case, we are working with height and weight column. So we need to make sure we have both column names in the same lower cases or upper cases. In my case, I have both in lower cases. So this command will check the missing values. Then we will pass the function catch missing values in height, comma, missing count, comma, number of missing count. So it will pass the argument that how many missing values we have. Replace this n with the actual number of missing values. Next, if we have missing values, we have to replace them. So at this time, I want missing values of the height column. If is dot na of the data into height, then impute missing values with the mean of that column. Mean data into height dot na.rm. That remove the missing values and compute mean of the column and then replace the missing value with the mean of height column. This curly bracket close here. It will work on the height column. Next, we have to check the weight column similar by using this similar statement. I will paste the same argument but replace the height with weight. Data into height, now it's weight, data into weight. Let's check we don't have any typo in the command. So these both conditions check the NA values in the weight and height column and replace with the mean of that particular column. Now outside this curly bracket, the main operation is to calculate BMI. So to calculate BMI, I don't need to mention again the entire equation. I already created this BMI calculate function. So I will use inside the loop that function like data into BMI. It will create a BMI column in my data like in data 1 or data 2. Then I call the function that will be calculate BMI. Inside this, I have to mention my columns that are data into weight. First argument is weight. Then the second argument is data into data selector height. Now pass the message that what message I want at this step. BMI has been calculated successfully dot with a number of data. Next is to save results in R. To do that, we have created the list that is result list. Here, result list, double square brackets and the file names. Next, we want to save results in our results folder. To do so, now we have to mention the output file path. Initially, we create input file path. Now, in the end, we will create output file path using the same file.path function. Here, we will mention output directory dot. Now, to save the results, we use this paste O function and the file names with which we want to save our results. Let's say I want to save results with BMI results data 1. So after this BMI results, comma, file names. So this paste O function will add the file names. These are data 1 and data 2. Next is write.csv. We want to save CSV files of this data, comma, output file path raw.names equals to false. And we'll pass the last message that is results save to output file path, comma. Now run this loop function and check what happened. Okay, unexpected symbol. Okay, I have added this percentage in inverted commas. That is wrong. It should be outside of the inverted commas. Let's run this loop again. So you can check the messages here. In data 1, we have 3 missing values in height column and 2 missing values in weight column. So these missing values will be replaced with the mean value of that column. BMI is successfully calculated and data saves into result BMI results data 1 CSV. Similar for we have similar messages for a data 2 CSV file where we don't have any missing value. So first check, do we have results in our result folder or not? Yeah, I have results in my BMI results data 1 and data 2 in my results folder. Now let's check these results in the R. Initially we create this result list that is empty. Now if I check at this time, we have data 1 and data 2 CSV file in it. So to access the result, we can use let's create a variable results1 and access the first element of the list from the list, that is a result list bracket double square bracket and 1. it will extract the result in result1 variable for the data1. Similarly, results2 for dataset2, result list, and element2, that is our dataset2. So we have result1 and result2 folder here. Initially we had 3 columns for data1: age, height and weight, but after calculating BMI we have another BMI column added here, and here you can see we don't have any NA values here in for the weight and BMI column, but we have NA value for the age because we didn't use this age column in our calculations, so this age column remains untouched. That's why here NA exists, but in this case we don't but in the case of height and weight column, now we don't have any NA values that we previously have in our original data set. Similar to this result to data 2, initially we have 3 columns: gender, height and weight. Now we have BMI column for their BMI. So you can see this is a very simple task to calculate the BMI, but the purpose is to show you how you can import your data, how you can assess and analyze your data within a loop structure. You can perform more complex things in within loops structure. You can run your entire machine learning pipelines or genomic data analysis. So you have to add multiple steps. But if you are going to run loop that has a lot of repetition or multiple steps, it is always better to try with the few repetitions, or you can before applying this into a multiple data sets, you have to check the results or output if if the loop is working fine or not before processing your actual data set. So I hope this session is informative for you. In the next session, we work with real gene expression data sets using a dplyr package. We will perform some data manipulation on it. Also, we will learn how you can download different data sets in R using public data repositories like ArrayExpress and NCBI. That's all for today. Thank you.